Right now, a telescope far beyond Earth has seen something that should not exist. In a speck of sky smaller than a grain of sand, it found hundreds of thousands of galaxies fully formed, massive, and impossibly early. Black holes grew too fast, structures appeared too large, and the universe turned out to be far bigger than we were ever told. This is not a new discovery. It is a warning, because if these images are real, then our timeline is wrong, our measurements are incomplete, and most of reality lies beyond what we can ever reach. What James Webb revealed doesn't just expand the universe, it exposes how little of it we truly understand. If you like what comes next, hit the like button and subscribe. What you are about to witness will change your view of the night sky forever. Let's begin. The universe we measured as 14 billion light-years across. Wrong, dead wrong. It actually spans 93 billion light-years, and every single discovery James Webb makes is forcing scientists to rewrite the textbooks. If you think you understand the cosmos, prepare to have your mind completely rewired. Let me hit you with something that'll make your brain hurt. Light left a galaxy called Jade's GSC 140 just 280 million years after the Big Bang. That light traveled through expanding space for over 13 billion years. James Webb captured it in 2025, and astronomers are still trying to process what they're seeing. Here's what makes this absolutely insane. The universe is about 14 billion years old today. This galaxy existed when only 2% of that time had passed. Think about that ratio for a second. If the universe's entire history was compressed into a single year, this galaxy formed on January 7th. We're literally looking at cosmic infancy. The discovery happened because James Webb hunts differently than older telescopes. It searches for something called redshift. When light travels across billions of light years, space itself expands. That expansion stretches the light waves, pulling them from visible colors into infrared radiation. The farther away something is, the more its light gets stretched. Jade's GSZ 140 has a redshift value of 14.44. That number represents extreme distance, beating the previous record holder by just 10 million years. What shocks scientists isn't just the distance. It's that this galaxy is bright. Actively bright. It's forming stars during a burst of rapid creation. Nitrogen levels inside it mirror ancient star clusters we see in our own galaxy today, suggesting star formation worked the same way even back then. But here's the problem. This should not be possible according to older models. Galaxies were supposed to grow slowly, carefully, over hundreds of millions of years. Jade's GSC 1420 proves they didn't. The universe had less than 300 million years to create this galaxy. 300 million sounds long, but in cosmic terms, it's a blink. For comparison, Earth has existed for 4.5 billion years. The dinosaurs walked around for 165 million years. This galaxy assembled itself in less time than that, and this is just the beginning. The Nancy Grace Roman Space Telescope launches in 2027, designed to scan massive portions of sky at once. It will likely find galaxies even farther back. Each new discovery pushes the boundary closer to the Big Bang itself, and every time we push that boundary, we discover something that shouldn't be there yet. Something forming too fast, shining too bright, existing too early. James Webb doesn't see like you see. It can't detect visible light. Instead, it captures infrared radiation, invisible to human eyes. This design choice is what makes the telescope so powerful for looking at the early universe. Without it, none of these discoveries would exist. Think about what you're actually seeing when you look at stars. You're seeing light that left those stars years ago. The nearest star beyond our sun is over for light years away. That means the light you see tonight left that star for years in the past. You're always looking backward in time when you look up. James Webb takes this principle to an extreme. It stares at objects so distant that their light has been traveling for over 13 billion years. The telescope is literally a time machine. Infrared vision matters because of expansion. The universe isn't static. Space grows larger every second. As it grows, it stretches everything inside it, including light waves. Light that started as ultraviolet or visible radiation gets pulled into longer wavelengths. By the time it reaches us, it has shifted completely into infrared. Objects from the early universe become invisible to telescopes that only see visible light. The Hubble Space Telescope couldn't find galaxies like Jade's GSC-140 because their light had redshifted beyond what Hubble could detect. James Webb sits at a location called Lagrange Point 2, about 930,000 miles from Earth. This position keeps it in permanent shadow from both Earth and the Sun, which is critical. Infrared sensors must be kept incredibly cold. If they heat up, they create their own infrared glow that drowns out the faint signals from distant galaxies. Webb's instruments operate at around -370 degrees Fahrenheit. That's colder than the surface of Pluto. The telescope's primary mirror spans 21 feet across. It's made of 18 hexagonal segments coated with gold. Gold reflects infrared light better than any other material. Each segment can be adjusted individually by tiny motors, allowing the entire mirror to focus perfectly. This precision means Webb can collect light from objects 100 times fainter than what Hubble could see. Here's how it finds early galaxies. Astronomers program Webb to observe specific patches of sky for hours or even days. The longer the telescope stares, the more faint light it gathers. Photons that left galaxies billions of years ago trickle in one by one. Webb's detectors count them. Over time, an image builds. Galaxies that would be invisible with a shorter observation become visible with patience. The spectrograph instruments then analyze the light. They split it into individual wavelengths, creating what scientists call a spectrum. Every element emits light at specific wavelengths, creating a unique fingerprint. Hydrogen looks different from helium. Oxygen looks different from carbon. By reading these fingerprints, Webb determines what a galaxy is made of, how fast it's moving, and most importantly, how far away it is. The redshift measurement comes from these spectra. It's the key to unlocking cosmic distance. And what makes this terrifying is the scale. Every deep field image Webb takes reveals thousands of galaxies. Each one is a world we will never visit, a place so far away that we're seeing it as it was when the universe was a child. Close your eyes and picture nothingness. That's what the universe looked like for its first few 100 million years. Darkness everywhere, no stars yet. No galaxies, just hydrogen and helium gas floating in the void, slowly clumping together under gravity's pull. Scientists call this era the Cosmic Dark Ages, and it lasted longer than anyone wants to admit. Then something changed. Gravity won. The gas collapsed into dense pockets. Pressure built, temperatures rose, and the first stars ignited. That moment ended the Dark Ages and began the Cosmic Dawn. Jade's GSC-1420 formed during this dawn, when light was just starting to flood the universe. 280 million years sounds like a long time. It's not. Not for building a galaxy. Think about the steps required. You need gas clouds to collapse. You need stars to form from that gas. You need those stars to cluster together. You need heavy elements to get created inside those stars, which takes multiple stellar generations. Each step requires time. Yet, Jade's GSC 140 completed all of this in under 300 million years. Here's what the universe looked like back then. Space was smaller, much smaller. Everything was closer together. The average temperature was higher because all that matter was compressed into less volume. Radiation from the Big Bang still filled the cosmos, though it had cooled significantly. Dark matter halos were forming, creating gravitational wells where regular matter could gather. These halos acted like invisible scaffolding for the first galaxies. The gas itself was almost pure hydrogen and helium. No oxygen yet, no carbon, no nitrogen, none of the elements that make up planets or life. Those elements had to be forged inside stars first. When massive stars exploded as supernovas, they scattered heavier elements into space. The next generation of stars incorporated those elements. This process is called stellar nucleosynthesis, and it takes time, multiple cycles, multiple explosions. What confuses scientists is that Jade's GSZ 140 already shows signs of nitrogen. That means at least 1 or 2 generations of stars had already lived and died inside this galaxy. In less than 300 million years, stars formed, burned through their fuel, exploded, enriched the gas around them, and allowed new stars to form with those enriched materials. The timeline is compressed almost impossibly tight. Compare this to our own galaxy. The Milky Way has existed for over 13 billion years. It's had time to go through countless cycles of star birth and death. It's had time to build up a rich inventory of heavy elements. Earth itself contains iron, silicon, gold, uranium, and dozens of other elements that didn't exist when the universe was young. All of that material came from ancient supernovas. Jade's GSC 140 started that same process in a fraction of the time. And it's not alone. James Webb has found over 100 galaxies from this same early period, each one bright, each one actively forming stars, each one challenging the models that predicted galaxies should form slowly. The cosmic dawn wasn't gradual. It was an explosion of activity. Galaxies appeared fast, shining intensely, transforming the universe from darkness into light within a few 100 million years. And we're only now seeing the evidence 13 billion years later because light takes that long to reach us. Imagine holding a grain of sand at arm's length and looking at the sky. The area that grain blocks contains almost 800,000 galaxies. That's what the Cosmos Webb survey revealed after James Webb spent over 200 hours staring at one patch of space. The survey covered about half a square degree of sky. For reference, the full moon covers about a fifth of a square degree. So we're talking about an area roughly 2.5 times the size of the full moon. In cosmic terms, this is microscopic. A tiny sliver. Yet, within that sliver, James Webb found more galaxies than most people can comprehend. 800,000 galaxies, each one containing billions or trillions of stars. Each one existing at different distances, meaning different times in the universe's history. Some are nearby, showing us galaxies as they look relatively recently. Others are so distant their light left them over 13 billion years ago. The survey essentially created a timeline of cosmic history, all visible in one image. The Cosmos Webb project used James Webb's near-infrared camera and mid-infrared instrument to capture the data. Astronomers chose the cosmos field specifically because it has very few foreground stars or gas clouds blocking the view. This gives a clear line of sight deep into space. The field has been observed by multiple telescopes over the years, including Hubble, but James Webb's infrared sensitivity allowed it to see galaxies Hubble missed entirely. What makes this survey revolutionary is its combination of width and depth. Many deep field images focus on extremely small areas, maximizing the observation time to see the faintest objects possible. Cosmos Webb sacrificed some depth to cover a larger area, revealing how galaxies are distributed across space. The result is a map showing galactic structures, clusters, and voids spanning billions of light-years. The image shows galaxies at every stage of evolution: spiral galaxies with elegant arms, elliptical galaxies that are smooth and featureless, irregular galaxies twisted by gravitational interactions, galaxies in the process of merging, their structures distorted as they collide, and everywhere, little red dots from the early universe, scattered like embers from the cosmic dawn. One unexpected finding is the sheer number of early galaxies. Before James Webb, models predicted far fewer bright galaxies in the first billion years after the Big Bang. The Cosmos Webb survey found 10 times more than expected. This suggests galaxy formation was more efficient and happened faster than theories predicted. The early universe wasn't empty and quiet. It was crowded and active. The survey also revealed structures forming earlier than anticipated. Galaxy groups and clusters that should have taken longer to assemble are already visible in the early universe. Gravity pulled galaxies together faster than models suggested. The cosmic web, the large-scale structure of the universe with its filaments and voids, was already taking shape when the universe was just a few billion years old. Each galaxy in the image has a story, each one formed through a unique combination of dark matter, gas collapse, and star formation. Some experienced violent mergers, some grew quietly over billions of years. Some are actively forming stars right now, their light showing the glow of young, hot stellar populations. Others are old and dead, their stars long since burned out, their light a ghostly echo of past activity. The Cosmos Webb survey will be studied for years. Astronomers will analyze individual galaxies, measure their distances, study their compositions, and track how they change over time. Every new analysis will refine our understanding of cosmic evolution. Every discovery will add another piece to the puzzle of how the universe grew from the Big Bang's fireball into the structured cosmos we see today. And this is just one patch of sky. There are over 40,000 square degrees across the entire celestial sphere. If every patch contains this many galaxies, the total number in the observable universe exceeds 2 trillion. That number is so large it loses meaning. We can't visualize 2 trillion. We can only understand it as a symbol of the universe's incomprehensible vastness. A reminder that we're seeing only the tiniest fraction of what's really out there, hidden in the darkness, waiting to be discovered. Right now, deep in the infant universe, something is feeding. A black hole weighing millions of times what our sun weighs is gorging itself on matter at a rate that breaks every law of physics we understand. It's eating 40 times faster than theory says is possible. And it's not alone. James Webb has found dozens of these cosmic predators lurking in galaxies that barely had time to form. The discovery is forcing scientists to confront an uncomfortable truth. Everything we thought we knew about how black holes grow is wrong. These monsters didn't slowly accumulate mass over billions of years like we believed. They appeared fast, hungry, and impossibly massive when the universe was still in its infancy. And the question keeping astronomers awake at night is simple but terrifying. How? The black hole that defies time? There's a black hole inside a galaxy with the clunky name CEERS 93316. The galaxy existed just 570 million years after the Big Bang. That alone is impressive. What makes it impossible is the black hole's size. It weighs millions of times more than our sun, and it's feeding rapidly, pulling in matter at a rate that shatters theoretical limits. Let me explain why this shouldn't exist. Black holes form when massive stars collapse. A star 20 times heavier than our sun can explode as a supernova, and its core implodes into a black hole weighing maybe 50 times what our sun weighs. That's a stellar mass black hole. It's tiny compared to supermassive black holes, which weigh millions or billions of times more. So how do you get from 50 to a million? You need time. Lots of time. The black hole has to eat. It has to consume gas, dust, and other stars over hundreds of millions or billions of years. Here's the problem. CEERS 93316 didn't have that time. The universe was barely 500 million years old when this galaxy existed. That's nowhere near enough time for a supermassive black hole to grow through normal feeding. Yet, there it is, confirmed by spectroscopy from James Webb. Not a theory, not speculation, real data. The galaxy belongs to a class astronomers call little red dots. These objects are small, faint, and extremely red because of their distance. James Webb has discovered dozens of them since operations began. Most confuse astronomers because they're either too dense with stars or they contain black holes too massive for their size. CEERS 93316 falls into the second category. The black hole outweighs the galaxy's stars by a significant margin. It's as if the black hole formed first and the galaxy is an afterthought. This ratio is called the black hole to stellar mass ratio. In the Milky Way, the central black hole weighs about 4 million times what our sun weighs. The galaxy's total stellar mass is around 60 billion times our sun's mass. The ratio is roughly 1 to 15,000. The black hole is a tiny fraction of the total. In typical massive galaxies, the ratio is higher. The central black holes weigh more, sometimes reaching billions of solar masses. However, the galaxies also weigh more, maintaining a similar proportion. The heaviest black holes sit inside the heaviest galaxies. The relationship holds across billions of years of cosmic time, except in the early universe. James Webb has found multiple galaxies where the black hole dominates. These little red dots consistently show black holes that are too massive for their hosts. The relationship between black hole mass and galaxy mass appears broken in the first billion years after the Big Bang. How did this happen? The little red dots mystery. James Webb started finding them immediately. Tiny red smudges scattered across deep field images. At first, astronomers thought they were just distant normal galaxies. Then the spectroscopy came back. These objects are not normal, not even close. They're compact, extremely luminous, and their properties make no sense according to standard models. Scientists call them little red dots, and they're rewriting the rules of early galaxy evolution. Over 100 of these objects have been identified so far. They all share common traits. First, they're small, much smaller than typical galaxies from the same era. Second, they're red because their light has been stretched by cosmic expansion. Third, they're bright, way too bright for their size. And fourth, they contain either extremely dense star clusters or massive black holes that shouldn't fit inside them. Here's what makes them bizarre. If you calculate the mass of stars needed to produce their brightness, you get a number that's impossibly dense. The stars would be packed so tightly that they'd collide and merge constantly. That doesn't happen in any galaxy we see today. Alternatively, if a supermassive black hole is producing the light, then the black hole is too big for the galaxy hosting it. In modern galaxies, black holes weigh about 1/10% of the galaxy's total mass. In little red dots, the black hole can weigh as much as the entire galaxy's stars combined. Both options break the models. Astronomers thought galaxies and their central black holes grew together, maintaining a balanced ratio. The galaxy forms first, building up stars over time. The black hole grows slower, feeding on gas that falls toward the center. Eventually, they reach equilibrium. Little red dots show this relationship inverted. The black hole got huge first, overpowering the galaxy around it. Another mystery is their abundance. Before James Webb, astronomers expected to find maybe a handful of unusual galaxies in the early universe. Instead, there are hundreds. They're not rare oddities, they're common. That means whatever process created them wasn't a fluke. It was a standard part of how the early universe worked. Some scientists think little red dots are transition objects. They might be catching galaxies in the middle of a growth spurt, when the central black hole is feeding rapidly, but the surrounding galaxy hasn't caught up yet. Over time, the galaxy might grow more stars and become a normal quasar. The bright objects powered by supermassive black holes that we see throughout the universe. If this is true, then little red dots are a snapshot of youth, a phase all galaxies go through before maturing. Others think they represent a completely different formation pathway. Maybe some galaxies form black holes first and build stars around them later. Maybe dark matter plays a bigger role than we realized. Maybe the early universe had conditions that allowed black holes to grow faster than they can today. One thing is certain, little red dots are not going away. Every new James Webb observation finds more of them. They appear at multiple distances, meaning they existed throughout the first billion years of the universe. They weren't limited to one specific time period. They were everywhere. The most unsettling part is what they say about our models. We built equations to describe how galaxies form. We ran computer simulations to test those equations. The simulations predicted slow, steady growth. They predicted galaxies forming stars over billions of years. They predicted black holes staying small relative to their host galaxies. Little red dots break all three predictions. LID 568, the physics breaker. Physics has limits. There are rules about how fast black holes can consume matter. These rules aren't suggestions. They're consequences of radiation, pressure, and gravitational forces. A black hole named LID 568 is ignoring those rules completely, and astronomers have no idea how. The black hole sits at the center of a dwarf galaxy, visible as it existed 1.5 billion years after the Big Bang. James Webb and the Chandra X-ray Observatory both observed it. The data came back clear. LID 568 is feeding at over 40 times the Eddington limit. That limit is the theoretical maximum rate at which a black hole can pull in matter, before its own radiation pushes that matter away. Here's how the limit works. When matter falls toward a black hole, it forms a swirling disk around the event horizon. Friction in this disk heats the matter to millions of degrees. Hot matter emits radiation, including intense X-rays. That radiation exerts pressure outward. If too much matter falls in too fast, the radiation pressure becomes strong enough to blow away the incoming material. The black hole essentially chokes itself, preventing faster feeding. This creates a natural speed limit. LID 568 is exceeding that limit by 40 times. 40, not 10% faster, not twice as fast, 40 times. That's like saying a car with a top speed of 100 miles per hour is somehow traveling at 4,000 miles per hour. The physics shouldn't allow it. One possibility is super Eddington accretion. This happens when matter falls in from all directions simultaneously, overwhelming the radiation pressure through sheer volume. Imagine trying to stop a tidal wave with a fan. The wave wins. If enough gas collapses onto the black hole at once, the radiation can't push it all away fast enough. The black hole gorges itself in a short, intense burst. These feeding frenzies are likely rare and short-lived. A black hole can't sustain super Eddington accretion for millions of years. The surrounding gas supply would run out. What makes LID 568 important is that astronomers caught it during this brief phase. It's a snapshot of rapid growth. The kind of event that might explain how supermassive black holes got so big so fast in the early universe. The black hole's mass is relatively small for a supermassive black hole, only a few million times heavier than our Sun. That makes sense, given how young the universe was when LID 568 formed. What doesn't make sense is how bright it is. The energy pouring out of the accretion disk is enormous. X-rays scream into space. The surrounding gas glows with heat. If this feeding rate continued for just a few million years, the black hole would double in size. Scientists think events like this might have been common in the early universe. Gas was denser back then. Galaxies were still forming, their structure chaotic and unstable. Massive gas clouds could collapse directly onto young black holes, triggering super Eddington feeding episodes. Each burst would add significant mass quickly. Over time, through multiple episodes, a black hole could grow from stellar mass to supermassive in far less time than normal accretion would allow. James Webb's discovery of LID 568 is critical because it provides evidence for this theory. Before this, super Eddington accretion was hypothetical. Now we've observed it, we've measured it. We know it happens. The question shifts from whether it's possible to how often it occurred. The universe is stranger than the equations suggest. Black holes don't always follow the limits we calculate. Under the right conditions, they break the rules, and in the early cosmos, those right conditions may have been everywhere. How black holes learned to run. A black hole is moving through space at 2 million miles per hour. It's not orbiting anything. It's not falling toward anything. It's running, fleeing, and it's dragging a trail of newborn stars behind it, like a cosmic scar, 200,000 light-years long. The black hole weighs 10 million times what our Sun weighs. That's supermassive by any measure. Yet something kicked it out of its home galaxy with enough force to send it rocketing through space at 3,000 times the speed of sound. James Webb confirmed this discovery in 2025, and astronomers are calling it the first verified runaway supermassive black hole. The object sits in a galaxy system that's actually multiple galaxies in the process of merging. When galaxies collide, their central black holes eventually sink toward the merged galaxy's center. Usually, in rare cases, gravitational interactions can eject one of the black holes entirely. That's what happened here. There are two ways to kick out a black hole this massive. First, when two supermassive black holes merge, they release gravitational waves. These waves carry momentum, and if they're emitted asymmetrically, they can give the resulting merged black hole a powerful kick. Think of it like recoil from a gun. The black hole gets pushed in one direction at high speed. Velocities can reach thousands of miles per second, more than enough to escape the galaxy's gravity. The second method involves 3 black holes. If a galaxy already had a binary pair of black holes at its center and a third black hole entered the system during a merger, the interaction becomes unstable. One of the 3 gets slingshot out. This is a 3-body problem, the kind of chaotic gravitational dance that has no stable solution. One black hole always loses and gets ejected. James Webb observed the black hole by detecting a bow shock in front of it. As the black hole plows through intergalactic gas at tremendous speed, it compresses the gas ahead of it, creating a shock wave, like a boat moving through water. That shocked gas heats up and glows. The telescope also detected the trail behind the black hole, a long filament where gas is collapsing and forming stars. The black hole's passage triggered star formation along its entire path. This is unprecedented. Stars forming in the wake of a runaway black hole. The gas gets compressed by the black hole's gravity as it passes, and that compression causes collapse. New stars ignite behind the fleeing giant. The trail is visible because young stars are bright. They shine in ultraviolet and visible light, and their light gets redshifted into infrared by the time it reaches us. The speed is mind-boggling. 2 million miles per hour. In 1 second, this black hole travels over 500 miles. It crosses the distance from Earth to the Moon in less than 2 minutes. At this rate, it will escape its galaxy system entirely and wander through intergalactic space as a rogue object. Galaxies without central black holes are rare, but this one is about to become homeless. What does this mean for our understanding of black hole evolution? Runaway black holes were predicted by simulations, but finding one confirms they exist. It also raises questions about how common they are. If galaxy mergers frequently eject black holes, there could be thousands of rogues drifting through space, invisible because they're no longer feeding on matter. The discovery also suggests black hole mergers in the early universe may have been chaotic. As galaxies formed and collided during the cosmic dawn, their black holes would have interacted violently. Some merged, some got ejected. The process was messy, unpredictable, and resulted in black holes scattered across the cosmos. The collision nobody saw coming. 2 black holes are colliding inside a galaxy system called ZS7. The system existed 740 million years after the Big Bang. Both black holes are supermassive, each weighing millions of times what our Sun weighs. They're circling each other, spiraling inward, and they will eventually merge into one even larger black hole. When that happens, the collision will shake space-time itself. James Webb detected the merger by analyzing the spectrum of light from ZS7. The data showed 2 distinct sources of energetic radiation very close together. Both sources displayed the signatures of accreting black holes, fast-moving gas, intense ionization, and broad emission lines from atoms swirling at incredible velocities. The 2 sources are separated by only a few thousand light-years, and they're moving toward each other. This is the most distant black hole merger ever detected. It's also the earliest in cosmic time. Previous mergers have been observed in the modern universe, but never this far back. The discovery confirms that black holes were already colliding and merging when the universe was less than 1 billion years old. This has major implications for how supermassive black holes grew so large so quickly. Mergers are one of the fastest ways to build massive black holes. Instead of slowly accreting gas over millions of years, 2 black holes can combine their mass in a single event. If mergers were common in the early universe, they could explain how supermassive black holes reached billions of solar masses within the first billion years after the Big Bang. The merger process itself is fascinating. As the black holes orbit each other, they emit gravitational waves. These are ripples in space-time predicted by Einstein's general relativity. The waves carry energy away from the system, causing the orbits to decay. The black holes spiral closer and closer, moving faster and faster until they collide. The final merger happens in a fraction of a second, releasing more energy than all the stars in the visible universe combined. We can't detect the gravitational waves from ZS7 with current technology. The waves are too faint after traveling over 13 billion light-years. However, future observatories will be able to. The Laser Interferometer Space Antenna, scheduled to launch in the 2030s, is designed specifically to detect gravitational waves from supermassive black hole mergers. When it becomes operational, it will observe events like ZS7 routinely. What makes this discovery critical is that it provides a preview of what LISA will detect. Before James Webb found mergers in the early universe, scientists thought events like ZS7 would be rare. Now they know mergers were common. That means LISA will detect far more gravitational wave events than initially predicted. The rate of black hole mergers in the infant universe was much higher than models suggested. The merger also tells us about galaxy evolution. ZS7 formed from two galaxies colliding and combining. As the galaxies merge, their black holes sink toward the center of the new combined galaxy. This process is called dynamical friction. The black holes interact with stars and gas, losing energy and spiraling inward. Eventually, they form a binary pair, which then merges. This sequence happens throughout cosmic history. Galaxies collide constantly. The Milky Way is currently on a collision course with the Andromeda Galaxy, and they'll merge in about 4 billion years. When they do, their central black holes will eventually merge as well. The process we see in G7 is the same process that will happen to our own galaxy in the distant future. The universe's youth was violent and chaotic. Black holes weren't patient. They didn't wait billions of years to grow. They found shortcuts. They merged. They fed at impossible rates. They dominated their host galaxies. And every discovery James Webb makes forces us to confront the same uncomfortable truth. The early universe didn't follow our rules. It wrote its own. Right now, 13 billion light-years away, there's a galaxy that shouldn't exist. It weighs 10 billion times what our sun weighs. It's filled with mature stars, dust, and complex chemistry. And it formed just 400 million years after the Big Bang, according to every model we built, every simulation we ran, every equation we trust. This galaxy needed at least 1 billion years to grow. It did it in less than half that time. James Webb keeps finding these impossible objects. Massive galaxies in the first billion years after the Big Bang. Not small dwarf galaxies, just forming their first stars. Large, well-developed systems containing billions of stars. They're everywhere, and they're forcing astronomers to confront a terrifying possibility. Everything we thought we understood about how galaxies form is fundamentally wrong. The galaxies that grew too fast. Galaxy formation is supposed to be gradual. Dark matter halos form first, creating gravitational wells. Gas falls into those wells, accumulating over tens or hundreds of millions of years. Eventually, enough gas collects to start forming stars. The galaxy grows slowly, adding more mass over time through continuous star formation and mergers with smaller galaxies. Reaching a mass equivalent to tens of billions of stars should take at least 1 billion years. Yet James Webb found galaxies with exactly that mass at redshifts of 9, 10, even 11. These galaxies existed when the universe was less than 500 million years old. Some appear as early as 300 million years after the Big Bang. Their mere existence challenges the timeline. One example is a galaxy observed at redshift 11. The data shows it contains 10 billion times the mass of our Sun in the form of stars and gas. This isn't a small galaxy. It's comparable in mass to the Large Magellanic Cloud, one of the Milky Way's satellite galaxies. The problem is the age. At redshift 11, the universe was only 400 million years old. Building 10 billion stellar masses in that time requires star formation rates far higher than models predict. The galaxies aren't just massive, they're also mature. Their spectra shows signs of older stellar populations, meaning the stars have been around for a while. Some galaxies even show evidence of dust, which forms from supernova ejecta. Dust takes time to accumulate. Its presence suggests the galaxy has already gone through multiple cycles of star formation and death. How did they grow so fast? One idea involves extremely efficient star formation. Maybe the first galaxies converted gas into stars at rates 10 or 20 times higher than modern galaxies. If star formation was that efficient, galaxies could reach large masses quickly. However, this requires explaining why efficiency was so high. What conditions in the early universe made star formation so effective? Another possibility is that dark matter halos grew faster than current models suggest. If halos assembled more quickly, they would pull in gas faster, accelerating galaxy growth. This could happen if dark matter has properties we haven't accounted for, or if the early universe's density fluctuations were stronger than we realized. Mergers might also play a role. If small galaxies formed very early and merged rapidly, they could combine their masses into larger systems in less time. However, mergers alone probably can't explain the most massive galaxies. The merger rate would need to be incredibly high, and there isn't enough time for that many mergers to occur. Some scientists think the observations might be misinterpreted. The masses could be overestimated if the galaxies contain very bright stars or active black holes that mimic the light of many stars. If that's true, the actual stellar mass would be lower, making the galaxies less problematic. However, spectroscopy generally rules this out. The light from stars has a different signature than light from black holes, and most of these galaxies show stellar-dominated spectra. Jade's GSC 1420, the Star Factory. There's a galaxy named Jade's GSC 140. It existed 290 million years after the Big Bang. James Webb measured its brightness and determined its forming stars at an absurd rate. The galaxy is creating new stellar mass 100 times faster than models predicted possible for its age. Star formation requires gas. Hydrogen clouds collapse under gravity, compressing until temperatures reach 10 million degrees. At that point, nuclear fusion ignites. Hydrogen atoms fuse into helium, releasing energy. A star is born. The process takes millions of years from start to finish, and it requires specific conditions. The gas must be dense enough. It must be cool enough. Turbulence must not disrupt the collapse. In the modern universe, galaxies form stars relatively slowly. The Milky Way creates about 3 new stars per year. That sounds fast, but our galaxy contains hundreds of billions of existing stars. The star formation rate is low compared to the total stellar mass. This is typical for mature galaxies. Most of their gas has already been converted into stars or expelled by stellar winds and supernovas. Jade's GSC 1420 is different. It's forming stars at a rate that would create the mass equivalent of hundreds or thousands of stars per year. For a galaxy that young and small, that rate is extreme. It means the entire galaxy is a star-forming furnace, with gas clouds collapsing simultaneously across its entire volume. Why is this happening? One theory involves cold streams of gas falling onto the galaxy from surrounding space. In the early universe, gas was distributed differently than today. Dark matter halos acted as gravitational wells, pulling in gas from vast distances. That gas flowed along filaments, streaming into young galaxies like rivers feeding a lake. The influx provided a constant supply of raw material for star formation. Another possibility is that the galaxy recently experienced a merger. When two galaxies collide, their gas clouds smash together, triggering massive bursts of star formation. The collision compresses the gas, causing widespread collapse. Star formation rates can spike by factors of 10 or more during these events. Jade's GSC 1420 might be caught in the middle of such a burst. The brightness is another mystery. Young stars are hot and luminous. They emit tremendous amounts of ultraviolet light. That light heats surrounding gas, causing it to glow. The combination makes the galaxy shine brightly. However, JDSG SC140 is brighter than expected, even accounting for its star formation rate. The light output suggests either the stars are unusually massive or there's another energy source contributing to the glow. Some astronomers think supermassive stars might be involved. These hypothetical objects would weigh hundreds of times more than typical stars. They would burn incredibly hot and bright, living only a few million years before exploding. If Jade's GSC 1420 formed a population of supermassive stars, their combined light would explain the excessive brightness. However, supermassive stars remain theoretical. No confirmed observations exist. The galaxy's spectrum shows strong emission lines from oxygen and hydrogen. This confirms active star formation. The lines are broader than expected, suggesting the gas is turbulent and moving at high speeds. This turbulence might be driven by stellar winds and supernova explosions. Young, massive stars die quickly and violently, injecting energy into their surroundings. That energy stirs up the gas, creating chaotic motion. What bothers scientists is the short timescale. At 290 million years after the Big Bang, the universe barely had time to form the first generation of stars, let alone build a massive star-forming galaxy. JADESGSZ 140 should be in its infancy, just beginning to assemble. Instead, it's fully active, producing stars at a breakneck pace. The search for the first stars. There's a galaxy where scientists might have found them, the very first stars to ever form. Population 3 stars, composed of nothing but hydrogen and helium. No carbon, no oxygen, no metals of any kind. Pure primordial material from the Big Bang. Stars are divided into populations based on their metal content. In astronomy, metals mean anything heavier than helium. Iron is a metal. Carbon is a metal. Oxygen is a metal. Modern stars contain a few percent metals by mass. These are called population I stars. Older stars contain less metal, maybe 0.1%. These are population 2 stars. Population 3 stars would have 0 metals, formed from the pure hydrogen and helium that existed right after the Big Bang. No one has ever confirmed a population 3 star. They should have existed, but they died billions of years ago. These stars would have been massive, burning through their fuel in just a few million years before exploding as supernovas. Those explosions scattered the first heavy elements into space, seeding the universe with materials for the next generation. Every star we see today, including our own sun, contains metals forged by population 3 stars. Finding them is hard because they're so old. Any population 3 stars still shining would be in the most distant galaxies, visible only as they existed in the early universe. Their light would be faint and redshift. Even James Webb struggles to detect individual stars at such distances. Instead, astronomers look for galaxies where population 3 stars might still dominate the stellar population. One candidate galaxy shows promise. Its spectrum shows almost no metal lines. The light is dominated by hydrogen and helium emission. This could mean the galaxy contains mostly population 3 stars. Though other explanations are possible, the galaxy might just have very pristine gas that hasn't been enriched by supernovas yet. Or the spectrum might be showing gas clouds rather than stars. Confirming population 3 stars requires deeper observations. James Webb needs to look longer, gathering more photons to detect fainter spectral features. If oxygen is completely absent, that would strengthen the case. Population 3 stars don't produce much oxygen because they explode before forming it. Later stellar generations create oxygen through fusion in their cores and release it when they explode. Why does this matter? Population 3 stars shaped the universe. They were the first sources of light after the cosmic dark ages. Their ultraviolet radiation ionized the surrounding hydrogen, transforming neutral gas into plasma. This process is called reionization, and it fundamentally changed the universe's structure. Without population 3 stars, reionization wouldn't have happened, and the universe would look completely different. These stars also set the stage for all future star formation. By creating the first heavy elements, they made planets possible. Carbon, oxygen, silicon, iron, all the materials that make up Earth came from supernovas of massive stars. Population 3 stars started that process. They were the cosmic alchemists, turning simple hydrogen and helium into the complex periodic table we rely on. Their masses are debated. Some models suggest they were hundreds of times heavier than our Sun. Others think they ranged from 10 to 100 times heavier. The difference matters because it affects how they exploded and what elements they produced. Very massive stars might have collapsed directly into black holes without exploding at all. If that happened, they wouldn't have enriched the universe with metals, delaying the formation of later stellar generations. James Webb's potential discovery offers a glimpse of what the earliest stars might have looked like. Even if this galaxy turns out not to contain population 3 stars, it shows that James Webb can detect objects pristine enough to be candidates. The telescope will continue surveying the early universe, and eventually astronomers will find definitive proof of these ancient giants. When that happens, it will complete the story of stellar evolution. We will have observed stars from every era, from the first generation to the current one. We will understand how stars changed the universe from a simple cloud of hydrogen and helium into the rich, complex cosmos we inhabit today. And we'll finally know how the first light pierced the cosmic darkness, setting everything in motion. Right now, 2 different measurements are telling us 2 completely different stories about how fast the universe is expanding. Both measurements are precise. Both have been checked repeatedly. Both use different methods, different instruments, different teams of scientists, and they disagree by enough that it can't be ignored. One of them has to be wrong, or worse, both could be right, which means our entire understanding of the cosmos is broken. Astronomers call this the Hubble tension, and James Webb just made it worse. The telescope confirmed what everyone feared. The discrepancy is real. It's not an error. It's not a fluke. Something fundamental is wrong with our model of the universe. And the answer might reveal forces and components we never knew existed, to numbers that don't match. The expansion rate of the universe is measured by something called the Hubble constant. It tells us how fast galaxies are moving away from us at a given distance. If the Hubble constant is 70, that means a galaxy 1 megaparsec away is receding at 70 kilometers per second. A galaxy 2 megaparsecs away is receding at 140 kilometers per second. The farther away something is, the faster it moves away. There are two main ways to measure this constant. The first uses observations of the cosmic microwave background, the faint glow left over from the Big Bang. This radiation fills the entire universe and carries information about the cosmos as it existed 380,000 years after the Big Bang. By analyzing tiny temperature variations in this radiation, scientists can calculate how fast the universe was expanding back then. They then use models to project forward to the present day. This method gives a Hubble constant of about 6. The second method uses nearby stars and galaxies. Astronomers measure the distance to galaxies using objects called Cepheid variable stars and type Ia supernovas. Both are well understood and can be used as distance markers. By measuring how fast these galaxies are moving away from us and comparing that to their distance, scientists calculate the Hubble constant directly. This method gives a value of about 73. 6 points is a huge difference. It's not a rounding error. It's not measurement uncertainty. Both methods are precise and have been checked repeatedly. The discrepancy is real, and it has persisted for over a decade. This is the Hubble tension. James Webb's role in this mystery is critical. One concern was that Hubble Space Telescope measurements might have errors. Maybe the distances were wrong. Maybe something about how Hubble observed Cepheid stars introduced a systematic bias. James Webb can observe the same stars with better sensitivity and resolution. If Hubble's measurements were flawed, Webb would find different values. Webb did not find different values. It confirmed Hubble's measurements. The distances are correct. The expansion rate really is about 73 when measured using nearby objects. The tension is not due to observational error. It's real. This leaves two possibilities. Either our model of the universe is incomplete, or something changed in how the universe expands over time. The standard model of cosmology assumes the expansion rate follows a smooth, predictable pattern determined by the amounts of matter, and dark energy in the universe. If those assumptions are wrong, the model breaks down. One idea is that dark energy behaves differently than we think. Dark energy is the mysterious force causing the universe's expansion to accelerate. It makes up about 68% of the universe's total energy. We don't know what it is, only that it exists. If dark energy's strength changed over cosmic history, that could explain the tension. The early universe might have expanded at one rate, while the current universe expands at a different rate. Another possibility is that there's an unknown component to the universe we haven't detected yet, some new form of energy or matter that affects expansion. This would be a major discovery, equivalent to finding a missing ingredient in the recipe for the cosmos. Or maybe the problem is with the cosmic microwave background analysis. Perhaps the models used to interpret that data are flawed. If the early universe was different than we assume, the projections to the present day would be wrong. The Hubble tension is one of the biggest puzzles in modern cosmology. It suggests our understanding of the universe is incomplete. Something is missing, something we haven't accounted for. And until we figure out what that something is, the tension will remain, a crack in the foundation of our cosmic models. When light stretches across time, light changes as it travels through expanding space. This isn't a minor effect. It's the reason James Webb can see the early universe at all. Without expansion stretching light into infrared wavelengths, the most distant galaxies would remain invisible forever. When a galaxy emits light, that light has a specific wavelength determined by the atoms producing it. Hydrogen emits a bright line at 121 nanometers, deep in the ultraviolet. Oxygen emits lines in the visible range. These wavelengths are fixed by physics. They don't change based on the source. However, as light travels through space, the fabric of space itself expands. This expansion pulls on the light waves, stretching them to longer wavelengths. Ultraviolet light becomes visible light. Visible light becomes infrared. Infrared becomes far infrared. The farther the light travels, the more it gets stretched. Astronomers measure this stretching using redshift, denoted by the letter Z. A redshift of 1 means the light's wavelength has doubled. A redshift of 2 means it has tripled. JADES GSC 140, the most distant galaxy ever found, has a redshift of 14.44. Its light has been stretched by a factor of 15.44. Ultraviolet light that left at 120 nanometers arrives at Earth at over 1800 nanometers, deep in the infrared. This is why older telescopes couldn't find these galaxies. The Hubble Space Telescope operates primarily in visible and near-infrared wavelengths, covering roughly 400 to 1600 nanometers. Galaxies with redshifts above 7 emit most of their light beyond Hubble's range. They're invisible to it. James Webb was designed specifically to solve this problem. Its instruments cover wavelengths from 600 nanometers to 28,000 nanometers, spanning visible red light through mid-infrared. This range captures light from galaxies at any redshift up to about 20. Beyond redshift 20, even James Webb struggles because the light shifts into wavelengths its detectors can't see. The expansion of space isn't like objects moving through space. It's space itself growing. Imagine dots on a balloon's surface. As you inflate the balloon, the dots move apart, not because they're traveling across the rubber, but because the rubber between them is expanding. Light traveling through expanding space experiences the same effect. The space between the light waves' peaks grows, stretching the wavelength. This expansion is accelerating. Dark energy drives the acceleration, pushing space to expand faster and faster. Galaxies far from us are receding at speeds that exceed the speed of light. This doesn't violate relativity because the galaxies aren't moving through space faster than light. Space between us and them is growing faster than light can cross it. For the most distant galaxies, their light spent over 13 billion years traveling to us. During that time, the universe expanded significantly. Space that was much smaller when the light began its journey is now vastly larger. The light waves stretched along with that expansion, transforming into infrared radiation by the time they reach James Webb's mirrors. Understanding redshift allows astronomers to measure distances with precision. If you know a galaxy's redshift, you can calculate how far away it is and how long ago its light was emitted. This turns the telescope into a time machine. Higher redshift equals greater distance equals farther back in time. The most extreme redshifts James Webb has detected are around 14 to 15. These correspond to galaxies seen as they existed just a few 100 million years after the Big Bang. The light from these galaxies has traveled across 99% of the observable universe to reach us. It's been stretched by factors of 15 or more, shifting entirely out of the visible spectrum. Without this stretching, we could never see the early universe. The galaxies would emit ultraviolet light that Earth's atmosphere absorbs before it reaches the ground. Even space-based telescopes operating in ultraviolet couldn't see them, because the distances are too great and the light too faint. Redshift transforms that ultraviolet light into infrared, a wavelength range where James Webb excels. The universe is revealing itself to us, not in the light it originally emitted, but in the transformed, stretched, ancient radiation that has crossed billions of light-years of expanding space. Every photon James Webb collects carries the signature of cosmic expansion imprinted on its wavelength, and every measurement we make reveals another mystery about how space itself behaves. Right now, as you read these words, you're made of atoms that were forged inside stars that died billions of years ago. The iron in your blood came from a supernova explosion. The calcium in your bones was created in the core of a massive star. The oxygen you're breathing right now was manufactured inside stars that lived and died when the universe was young. You are literally made of stardust. And James Webb is showing us the cosmic furnaces where those atoms were born. Every discovery the telescope makes isn't just about distant galaxies or ancient black holes. It's about us, our origin story, the chain of events that led from the Big Bang to this moment, where conscious beings made of recycled star material can look back across 13 billion years and witness their own cosmic ancestry. This is the most profound realization James Webb offers. We are the universe observing itself, the cosmic dark ages and first light. For hundreds of millions of years after the Big Bang, the universe was completely dark. No stars existed, no galaxies, just neutral hydrogen gas filling all of space, cooling as the universe expanded. Scientists call this era the cosmic dark ages, and it ended when the first stars ignited. That moment, when light flooded the cosmos for the first time, is called the cosmic dawn. It happened roughly 150 to 300 million years after the Big Bang. Gravity pulled gas into dense clumps, pressure built, temperatures rose, fusion ignited, and stars began to shine. The first stars were different from modern stars. They formed from pure hydrogen and helium, with no heavier elements. This affects their structure and evolution. Without metals to facilitate cooling, the gas clouds couldn't fragment into small pieces. They collapsed into larger, more massive objects. The first stars were likely 50 to several hundred times heavier than our Sun. These massive stars burned incredibly hot and bright. They emitted huge amounts of ultraviolet radiation, far more than smaller stars produce. This radiation began to ionize the surrounding hydrogen gas. Neutral hydrogen atoms absorbed the ultraviolet photons, losing their electrons and becoming ionized plasma. A bubble of ionized gas formed around each star, growing larger as more photons streamed out. At first, these bubbles were isolated. Stars formed in scattered locations across the universe, each creating its own ionization zone. The regions between remained dark and neutral. Over time, more stars formed, more bubbles appeared. Eventually, the bubbles began to overlap, merging into larger ionized regions. This process is called reionization. It transformed the universe from a neutral gas-filled void into an ionized plasma. Reionization took hundreds of millions of years to complete. Early on, only small patches of space were ionized. By about 400 million years after the Big Bang, most of the universe had been reionized. The cosmic dawn transitioned into an era of intense star formation and galaxy growth. James Webb is observing galaxies from the cosmic dawn. These galaxies contain the descendants of the first stars. What we see in these galaxies is the early phase of structure formation, when the universe was just beginning to light up. The light from these galaxies is faint and redshifted. It has traveled across 13 billion light-years of expanding space to reach us. When the light left those galaxies, the universe was young and small. Now it's old and vast. The light carries information about what conditions were like during the cosmic dawn, encoded in its spectrum and brightness. Observations of this era help answer fundamental questions. How quickly did the first stars form? How massive were they? How efficiently did they ionize the surrounding gas? These questions affect our understanding of everything that came after. The first stars set the stage for all subsequent cosmic evolution. Reionization also affected how later galaxies formed. Once the universe was ionized, small clumps of gas couldn't easily collapse to form stars. The ionized gas has higher pressure, resisting gravitational collapse. This suppressed star formation in low-mass halos, preventing the formation of very small galaxies. The cosmic dawn was a turning point. Before it, the universe was simple: hydrogen, helium, dark matter, and radiation. After it, the universe became complex. Stars, galaxies, heavy elements, and the structures we see today. That transition happened in just a few 100 million years, a brief moment in cosmic history, our place in the cosmic story. The scale of what James Webb reveals is almost incomprehensible. 2 trillion galaxies in the observable universe, each one containing billions or trillions of stars. Many of those stars have planets. The number of potentially habitable worlds exceeds comprehension. If even a tiny fraction of those worlds develop life, the universe could be teeming with it. We're not special in terms of location or uniqueness. We're one planet among countless others, yet we're also unique in our ability to observe and understand the cosmos. No other species on Earth has built telescopes or developed physics. No other known life has deciphered the universe's history or measured its age. Intelligence capable of scientific discovery may be common in the universe, or it may be incredibly rare. We don't know. What we do know is that we have it, and we're using it to explore our origins. The atoms in your body were forged in stars that lived and died billions of years ago. James Webb sees the light from those ancient stars, photons that escaped just after the cosmic dawn. The discoveries also reveal how much we still don't understand. Dark matter makes up most of the universe's mass, and we have no idea what it is. Dark energy drives cosmic expansion, and we don't know its nature. The Hubble tension suggests our cosmological model is incomplete. Supermassive black holes grow faster than models predict. Galaxies form earlier and brighter than simulations allow. Every answer raises new questions. This is the nature of science. We build models to explain observations. New observations challenge those models. We revise the models, making them more accurate. Then new observations challenge the revised models. The process repeats endlessly. We approach truth without ever fully reaching it. Each generation of scientists gets closer, but there's always more to learn. The discoveries remind us of our cosmic insignificance. We live on a tiny planet, orbiting an average star in an ordinary galaxy in an unexceptional part of the universe. Our galaxy is one of trillions. Our star is one of hundreds of billions in that galaxy. Earth is one of potentially billions of habitable planets just in the Milky Way. The scale dwarfs us. Yet this insignificance is also liberating. The universe doesn't revolve around humanity. Cosmic events unfold according to physical laws that don't care about us. Black holes merge, galaxies collide, stars explode. These processes happened long before humans existed and will continue long after we're gone. We're observers, witnesses to a grand drama that transcends our existence. The universe observing itself, looking at James Webb images, seeing galaxies billions of light years away, recognizing that we're viewing the universe as it existed in its youth. This provokes a sense of awe that transcends scientific knowledge. It touches something deeper, a recognition of beauty and mystery that goes beyond equations and data. The universe is incomprehensibly large. It's incomprehensibly old. It operates on scales of time and distance that our minds struggle to grasp. Yet we've reached out with our instruments and our intellect, peering across billions of light years to witness the cosmos in its infancy. We've decoded the light from ancient galaxies. We've measured the masses of black holes that formed before Earth existed. We've traced the history of the universe from the Big Bang to the present. This is humanity's greatest achievement, not the construction of cities or the invention of technology, but the understanding of our place in the cosmos. We are small, we are brief, we are insignificant, and yet we're capable of comprehending the universe itself. That paradox defines our existence. We are the universe become conscious of itself. Matter organized in a way that allows it to study matter, atoms contemplating atoms. James Webb has shown us a universe stranger and more magnificent than we imagined. It has raised questions we don't yet know how to answer. It has revealed structures we don't yet understand. And it has reminded us that despite our smallness, we have the capacity to explore, to discover, and to wonder at the impossible vastness of everything that exists. The journey isn't over. More galaxies wait to be discovered. More mysteries demand solutions. The universe keeps its secrets well, but slowly, patiently, we're learning to read its story, written in light that has traveled for billions of years, carried by photons that began their journey when the cosmos was young, and arriving now, at this moment, to be captured by mirrors made of atoms forged in those ancient stars. We are stardust, looking back at our own birth.